Hey everybody, welcome back. This is Chem 103, Chapter 4. We're talking about models of the atom, and we are setting the foundation for talking more about the periodic table and periodic trends in Chapter 5. We're going to do a little bit of a history lesson. We can't talk about models of the atom without going way back to Greek philosophers. The ideas that led up to the atomic theory that we know today actually go way back to about 400 BC. Greek philosopher Aristotle argued that matter is continuous. And what that means is that it can be broken apart an infinite number of times. That's what continuous means here. Democritus argued that matter is discontinuous, that at some point you can't subdivide matter any longer. And what he called that point where you can no longer divide matter and have it still be matter, he called that point atomos. So that's where we get atom from. Quite a bit later, we've got John Dalton. And in 1803, he published the first atomic theory. He had 5 postulates, which just means 5 points. So these were the 5 things that he said must be true about atoms. Elements are composed of tiny, indivisible, indestructible particles called atoms. Now we'll see here that some of the things that Dalton proposed were incorrect. One of which is that he said atoms were indivisible. We'll see that you can divide atoms into subatomic particles. So he wasn't right there, but they are tiny and you can't destroy matter. So he got 2 things out of 3 right in this first postulate. He also said that all atoms of an element are identical and have the same properties. So if you have an aluminum atom that you found in North Carolina, if you find one in South Carolina or Georgia or Tennessee, they're all going to have the same properties. Atoms of different elements combine to form compounds. And we already kind of know that to be true because in Chapter 3, we talked about what compounds are, and they're chemically combined elements. These compounds contain atoms in small whole number ratios. So you're not going to have half an atom of oxygen. You're always going to have whole numbers of elements combined to make compounds. Atoms can combine in more than one ratio to form different compounds. Now, that may sound a little bit more complicated than it really is. Let's take hydrogen and oxygen. If we have 2 hydrogens and 1 oxygen, we already know what that is. It's water. But what if I have 2 hydrogens and 2 oxygens? Well, that's something totally different. That's hydrogen peroxide. And if you've ever gotten a cut or a scrape or anything like that playing outside as a kid, somebody might have brought out that brown bottle. That's hydrogen peroxide. These are the 5 postulates that Dalton put together for his atomic theory. You'll need to know all 5 of these, and you'll also need to know where Dalton was wrong. Moving along, we've got J.J. Thomson. So he did work with cathode rays, and he determined the charge to mass ratio of cathode rays, and he was credited with the discovery of the electron. So pretty smart dude, okay? He also had students working with him, for him, under him, however you want to say it. And his lab, they put together this model called the plum pudding model of the atom in 1903. And what he proposed was that electrons, which he discovered, remember, were distributed evenly throughout this homogeneous sphere of positive charge. Now, it's called the plum pudding model because, well, this yellow here, think of that as the pudding. It's a sea of positive charge. And the electrons were the plums. So you could just kind of see the electrons if you could see an atom. You could see the electrons kind of dotted throughout this space, distributed evenly in this sphere of positive charge. That was his proposal of what the atom looked like. We're going to jump forward a little bit, and then we're going to jump back. So a few years later, Robert Millikan determined the charge of an electron. And with that information, J.J. Thomson was then able to calculate the mass of the electron and the mass of the proton. And you may be saying, proton? We ain't talking about no protons yet. You're right. So that happened after another very key event. J.J. Thomson, as I mentioned, had graduate students. Okay, the equivalent of graduate students, what we would call today. Ernest Rutherford was one of them. And once Ernest had enough training, he went on and had his own lab, and he had a student named Hans Geiger. And they put together what's called the gold foil experiment to test J.J. Thomson's plum pudding model. And what they did was they fired alpha particles, which are pretty big, at thin gold foils. And their hypothesis was that if the plum pudding model is correct, these alpha particles should pass straight through undeflected. There shouldn't be anything in there big enough to deflect these large alpha particles, because this sea of positive charge was really just empty space. And electrons were so small, they're not going to deflect a large alpha particle. So this is kind of a picture of what their setup was. They had a block of lead, which is a source of alpha particles. So they would shoot a beam of alpha particles at this thin foil, and they had a circular fluorescent screen that could detect where the alpha particles ended up after they went through the foil. Most of those alpha particles went straight through. They were undeflected, which means that they didn't encounter anything massive enough to change their direction. However, a number of the alpha particles were deflected, and sometimes at very large angles. So if you're going straight, and then all of a sudden you come out like this or like this, that's a major deflection. So that means the alpha particle must have encountered something big enough to cause it to change direction. Most of those particles pass through empty space because atoms are largely empty space. But these results supported the idea that there is an atomic nucleus. And it's at the center of the atom. When an alpha particle struck the nucleus, it would be deflected. So it might bounce backward, or its angle might be changed drastically. With this new discovery, Rutherford put forth a new model of the atom. And that said, Yeah, we've got electrons in this mostly empty space, but at the center, there's a nucleus. And in that nucleus, we have the positively charged protons and the neutral neutrons. They don't have a charge. So with this, Rutherford knew, okay, there's got to be something more than just these protons in here. So he postulated there must be something like a neutron. But neutrons were discovered in 1932 by James Chadwick. So these are the subatomic particles: electrons, protons, and neutrons. You've probably heard these before, somewhere in your schooling, but if it's not super familiar to you, that's okay. This table is very helpful because it gives you just the basic information about each of these subatomic particles. You'll need to recognize these symbols because I'll use them throughout our lecture, both here with the pre-recorded lecture and also in live lecture when I'm writing things out and we're going through problems. Then we've got the location. Electrons are outside of the nucleus, protons and neutrons are inside the nucleus. The relative charge. Electrons are negatively charged, protons positive, neutrons no charge. Then we have their relative masses. Protons and neutrons have about the same mass. Electrons are super duper small. You do not need to know the exact numbers in this column. You just need to know, relatively speaking, electrons super small, protons and neutrons about the same size. So if you're someone who likes to put tables into your notebook or recreate them in your notebook, this would be a good one to have. Now we can talk about atomic notation, since we have subatomic particles under our belts. Each element has a characteristic number of protons in its nucleus, and that number is the atomic number. It's abbreviated as Z. When you're writing an element in atomic notation, that number goes here. So we've got the symbol of our element, and then bottom left, atomic number. The total number of protons and neutrons in the nucleus is called the mass number, and you'll see that as A. The mass number is above the atomic number in atomic notation. Now, don't get this confused with the periodic table. Atomic notation does not appear on the periodic table. And likewise, mass number does not appear on the periodic table. We do, however, see the atomic number. So what we're talking about is atomic notation, where you're writing something down and you want to, with shorthand, talk about an element that has a specific number of protons and neutrons in its nucleus and a specific atomic number. We haven't talked about electrons yet. In a neutral atom, and I'm stressing neutral because we won't always be talking about neutral atoms. Hint to chapter 5. In a neutral atom, the number of protons is equal to the number of electrons. So you have the same number of protons as you do electrons. I would recommend having the atomic notation example in your notebook, along with the relationship between the number of protons and electrons in a neutral atom. When we go through and do some practice, and I show you how to use the symbol and the atomic notation, you should have an example too. We'll practice doing this in class as well. So here's an example. I have silicon. There's a 29 up top and a 14 down below. The 14 is the atomic number, and that tells us how many protons. The mass number is 29. That tells us the number of protons plus the number of neutrons. If I take the mass number, which is 29, and subtract the number of protons, so this is our A minus Z, then that gives us the number of neutrons, which is 15. Now, within atomic notation, the number of electrons is not listed, but we can still figure it out for a neutral atom. The number of protons is equal to 14. That means we've got 14 electrons. Remember, a neutral atom means there's no charge. So if we have a positive 14 charge from our protons, we have to have a negative 14 charge from our electrons. The reason why we need atomic notation is because of the existence of isotopes. An isotope is just an atom of the same element with a different number of neutrons. So most of the elements that we're familiar with, they have isotopes. They have different numbers of neutrons, but the same number of protons. When you want to talk about an isotope, you have to use the different mass numbers. Otherwise, you won't know. One example would be magnesium. Magnesium, you can talk about magnesium 24, magnesium 25. Those are isotopes. With that one, 24 is equal to the mass number. And here, we've got 25 is equal to the mass number. So we can talk about isotopes of the same element. Here's a table that shows you many of the isotopes that exist. So there's isotopes for hydrogen, helium, lithium. The list goes on. This is just the first 10 elements. Oftentimes when we refer to an isotope, we write the name of the element and the mass number. So for example, if we've got carbon, you can write carbon and then a dash and then 12. You can also write the atomic notation. And that will give your reader more information because you've got the mass number and the atomic number. But what else do you see when you look at a periodic table? Above the symbol, you'll see the atomic number. That tells you how many protons. But below it, you'll see a decimal number. Just as a reminder, that's the atomic number, and it's always a whole number. No decimals. Same with the mass number. But below, we have the atomic mass. And the atomic mass just gives us the weighted average of the mass of all the known isotopes of that particular element. A weighted average is different from just a regular average. For a regular average, let's say that we had carbon, right? We had carbon-12 and carbon-13, two isotopes. What a regular average would do is assume that I've got two isotopes and they're each represented equally. So half of the carbon that you see in the world is carbon-12 and the other half is carbon-13. While that's technically possible, it's not true. There's usually one isotope that's favored or two isotopes that are favored versus some others. That's why we use a weighted average. The weighted average takes into account the percent abundance of each isotope. So the weighted average is going to be closest to the mass of the isotope that is in the highest abundance. What does that mean? Let's say that we had carbon-12 and carbon-13, and instead carbon-12 was like 80% abundant. Which leaves only 20% abundance for carbon-13. And the mass of carbon-12, we'll just make it easy and say that it's 12 atomic mass units, which we'll talk about in a second. And carbon-13 is 13. With the regular average, you would take 12 plus 13 and divide it by 2. So that'd be 25 divided by 2, which will give you 12.5. However, with a weighted average, we're saying I'm going to take my mass of my isotope and multiply it by the percentage of abundance. And I'm going to do that for each of my isotopes. When you do that math, you get 12.2. So that's a regular average versus the weighted average. When you're doing your homework, make sure that you do a weighted average, not a regular average. Because what this shows is that it's closest to the mass of carbon-12. Because there's more carbon-12, so the mass of carbon-12 has a greater effect on the atomic mass of carbon. Now that was just a play example. Let's use some real numbers. Gallium has two isotopes, gallium-69, gallium-71. We have the masses of each isotope and the abundance. What I like to do is draw a table and then I can put together my equation. So you can see the equation here, but I'm going to show you how to get there. I put all of the information together. So we've got the isotope, the atomic mass, percent abundance, and then I also write the percent abundance as a decimal. For gallium-69, we can fill in everything from our problem. The atomic mass, and I'll do a little bit of highlighting here so you can trace. We're going to do atomic mass in yellow. Percent abundance in green. So you can see where that information came from. And you see this AMU, that stands for atomic mass units. Atoms are so small that this is what chemists and others use when we're describing the mass of an atom. Just filling in the chart here. So that's all the given information. Remember that a percentage is part out of 100, right? So if you take the percentage and divide by 100, then you'll get the percent abundance as a decimal. When you divide by 100, you are moving the decimal point 2 places to the left. So 60.11 becomes 0.6011. 39.89 becomes 0.3989. We can take these numbers, the decimals, and multiply by our atomic mass. And that will give us what we're looking for, which is the average atomic mass. It's the same thing as weighted average. You have to know that when you're calculating the atomic mass, you're using a weighted average. The first part of this equation deals with the contribution of the gallium-69 isotope. The second part deals with the gallium-71 isotope. More than half of the gallium is the 69 isotope. So the mass is closer to the mass of the 69 isotope. Let that sink in. We'll work another couple of problems in class. But I do recommend that you put out all the information into a chart so that it's organized, and then you can fill in your equation. You may have more than 2 isotopes to work with. So if you have 3 or 4 or 5 isotopes, then you need to organize all of that information so you're not using, you don't want to pair up the numbers improperly. Because if I switched and I used the 39.89% with the gallium-69 isotope, I would get a totally different number. So your bookkeeping skills are going to be very useful here. Stay organized, make a chart, then touch your calculator. Now we're looking at the periodic table a little more closely. We can use the periodic table to find the atomic number. Like I said before, the atomic number is the number that is above the symbol. So capital C is the symbol for carbon. The periodic table that I'll provide for you will also have the element name spelled out fully underneath the symbol. Underneath that, you have the atomic mass. Remember that that is the weighted average. So it takes into account the abundance, not just how many isotopes there are. With the information from the periodic table, we can think about what a carbon atom looks like. The atomic number is 6, which means that we have 6 protons. And that's what the little red guys are. Protons are in red. For a neutral atom, you've got 6 electrons, which the electrons are not shown. And you can also have 6 neutrons. So protons are always red, neutrons are always blue. In thinking more about electrons and their placement in the atom, we first have to talk about the wave nature of light. Light travels through space as a wave, and waves can be described by their frequency and their wavelength. So let's say that we had this wave. The wavelength is the distance that the light wave travels in one cycle. And that's typically measured in nanometers. What does one cycle mean? One cycle means peak to peak or trough to trough. It's the same distance. But if you measure from here to here, that is a wavelength. And the little symbol that I just drew, that's a lambda. You'll see that as the symbol for wavelength. If you took physics, this is probably not news to you if you remember the physics that you encountered. Otherwise, it might be new. The other bit of information that we need to talk about is the frequency. And the frequency is the number of wave cycles that you complete in each second. That means how many wavelengths, how many peak to peaks or trough to troughs can I complete in 1 second. Light travels at a constant speed of 3 times 10 to the 8th meters per second, which is ridiculously fast. There are characteristics of long wavelengths and short wavelengths. If you have a long wavelength, like this red one on top, then you have a low frequency and low energy. So let's write that out. I like to make tables, so I would recommend putting this information in a table if it's not familiar to you. Long wavelength, we've got my down arrow means low or decreased, so low energy, and low frequency. I abbreviate frequency with an F. Kind of a fancy F. It's got a little curly tail. If, however, you have a high energy wave, then it's a shorter wavelength. So we've got high energy, and a high frequency. And if you look at the distance in the top long wavelength, that is one wavelength. And that distance we can fit 3 wavelengths of the other. Just for comparison's sake. So long wavelength, low energy, low frequency. Short wavelength, high energy, high frequency. And this is all relative. There's a radiant energy spectrum. You may also hear it called the electromagnetic spectrum. They're the same thing. It's an uninterrupted band, which means it's a continuous spectrum. On the left-hand side, you have the short waves, and they are high energy and high frequency. On the right-hand side, we've got those long wavelengths, which are low energy and low frequency. So moving from left to right, we're decreasing in energy and increasing the wavelength. You will need to know all of these different types of waves, but you don't need to know specific numbers for the wavelengths. Just know the relative order. So the highest that we have on this chart is cosmic rays. Very short wavelengths, very high energy. Followed by gamma rays, X-rays, which X-rays you, I'm sure, have heard of if you've ever been to the dentist. There are dental X-rays. If you've ever broken a bone or thought you broke a bone, then you may have had an X-ray as well. Then there's ultraviolet light, abbreviated UV. So that comes from the sun. That's why you put on sunscreen. That's why you wear sunglasses, to protect your eyes and your skin. Then there's the visible light spectrum, which is the rainbow, right? All the colors that we see. You'll need to know those different colors and kind of where they stand. So I learned the rainbow, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. The way that this chart shows you the rainbow, however, is in the reverse order. So as long as you know that red light is the longest wavelength out of the visible spectrum, violet is the shortest, then you should be good to go with all the colors in between, if you know your rainbow. After visible light, we've got infrared, then microwaves, TV, and radio. Again, make sure you know the relative order of these so you can answer a question like which of these is the highest, wavelength, right? Or the shortest wavelength. Then if I said cosmic rays, infrared, or TV, you would say, oh, cosmic rays, that has the shortest wavelength. Or which of those 3, cosmic, infrared, or TV, has the lowest energy? You'd say, oh, TV. So that's what you need to know for the radiant energy spectrum. Don't have to know numbers. Just know, relatively speaking, when you compare them, what's what. Again, the visible spectrum, we're talking about the wavelengths that can be detected by the human eye. So if you take light and you split it with the prism, you can detect all the colors of the rainbow. Now this is related to the quantum concept, and we're going to put the two together in just a minute. The quantum concept states that energy is present in small, discrete bundles. So if you have a tennis ball or any kind of ball, and you've got a ramp and a set of stairs, if you set that ball at the top of the ramp, it'll just roll, right? It'll just roll all the way down. It'll continuously lose potential energy, increase in kinetic energy, roll down the ramp. However, if you had a tennis ball that you placed on top of a set of stairs and you gave it enough of a push so that it would fall down each stair one by one by one, that ball is going to lose its potential energy in small little bundles. The ball can't fall down half a stair. It can't fall down 3/4 of a stair. It either falls all the way and makes it all the way down to the next step, or it's still on the same step. It has to have a specific amount of energy to get from step 1 to step 2. And if it doesn't, it's not going anywhere. That's the quantum concept. Stay with me. A little bit more history, then we'll put the quantum concept together with the idea of light. Niels Bohr, he speculated that electrons orbit around the nucleus in fixed energy levels. That really means that electrons are found in specific energy levels and nowhere else. There's no in between. So if you have energy level 1, which energy levels are referred to as N, then there's N equals 2. N equals 1.5, that doesn't exist. Specific discrete energy levels. And those energy levels, that's called quantized, the same idea with the stairs. You either fall all the way off the step onto the next step, or you're still on the same step. It's the same with electrons. They're not hanging out between energy levels. You're either in this energy level 1, or you're in 2. There's no in between. One piece of evidence that corroborates this theory is the emission line spectra of elements. When you have an element in a sealed tube and you excite it so that it's a gas, right? Pass some voltage over it, you're going to cause that gas to get excited, and then it's going to release light. That light, if you filter it through a slit and then have that light go through a prism, it will break up that light into colors. Each element has its own set of specific colors that it will show when you do this. So for hydrogen, you see a violet line, blue, green, and red. Everywhere else is dark. Remember that the colors are continuous, but these discrete little packets of energy that are released from elements when they're excited and then they drop back down to a ground state, that's not continuous. You see discrete bands of light. And remember that each of these colors of light is associated with energy. Let's write that down. Each band of light is associated with a specific energy. So the idea of these emission spectra, it's like an atomic fingerprint. Light is continuous, and that's what's shown here at the top. So we've got the whole gamut of colors that you could potentially see. But when you heat up an element and excite it, and it releases those packets of light, you're only seeing discrete bands. And each element has its own unique set of bands that it will show. So this was evidence that electrons can only exist in certain energy levels and not in others. What we understand now is that there are different energy levels. Energy level 1, 2, 3, and so on up to 7. So for the rest of this lecture, we're going to talk about these energy levels, give you some more vocabulary, and eventually we're going to be able to talk about where the electrons are around an atom that's neutral and ground state. So we talked about energy levels in that last slide. And energy levels, those are N. Okay. Within that N, electrons occupy energy sublevels. So if you think about the floors in a mall, like an indoor mall, each floor is a big floor. It's all mall, right? But each floor is broken up. So you've got clothing stores, and maybe you've got a bundle of clothing stores all around each other. You got the food court, you got shoe stores, you got Sephora. Like, everything is organized, and there's kind of clusters of things on the same floor. It's all the mall, all level 1, but there's different compartments. That's the same thing with these energy sublevels. The sublevels are called S, P, D, and F for sharp, principal, diffuse, and fine lines that you see in the emission spectra. So that's the colors that we were talking about just a few slides ago. The number of sublevels in each level is the same as the number of the main energy level. So N, we can also call that the main energy level. So if I have N equals 1 as my main energy level, then it has 1 sublevel. If I have N equals 2, it has 2 sublevels. The first energy level, N equals 1, has 1 sublevel, and that is 1s. The second energy level has 2, just like I said. That's N equals 2. That's got 2s and 2p. The third energy level has 3. The 1 tells you the energy level. That letter tells you the sublevel. And it's the same thing in all of these. Oops. The number is the energy level. The letter is the sublevel. all of the electrons of the same energy are going to be in the same energy level. They'll just be broken up into these different sublevels. The maximum number of electrons that any sublevel can hold is 2 electrons. I should say orbital, because we've got multiple orbitals that equal a sublevel, and we haven't covered orbitals just yet. But the S sublevel holds a maximum of 2 electrons, and it contains 1 orbital. The P sublevel holds a maximum of 6 electrons, and it has 3 orbitals. The D sublevel holds a maximum of 10 electrons, and there are 5 orbitals. The F sublevel holds a maximum of 14, and there are 7 of those in the F sublevel. So in terms of size, we've got the orbital, which is the smallest, and the orbitals come together to make a sublevel. The sublevels come together to make a main energy level. So if we have n equals 1, that's our main energy level. The sublevel would be 1s. The orbital, we'd also call it 1s. If I had n equals 2, let's say I wanted to talk about the p orbitals. 2p would be the sublevel. The orbitals would talk more about the geometry, 2px, 2py, and 2pz. And this will make a little more sense when I show you the different shapes of the orbitals. But this is to give you an idea of the difference between what a main energy level is, a sublevel, and an orbital. Each orbital holds 2 electrons. So notice how I was putting along the side, the S sublevel has 1 orbital. Well, 1 orbital times 2 electrons gives you 2 total electrons in that sublevel. The P sublevel has 3 orbitals. So 3 times 2 electrons in each of those gives you 6. That's your maximum. The D has 5. So 5 orbitals, 2 electrons each gives you 10. The F has 7 orbitals. Each of those holds 2 electrons. That gives you 14. There's a lot of information here, and it can be a little bit overwhelming. But with the practice problems, it'll help you synthesize all of this information into something that's usable that you can apply. There's a lot of little details here and there, and you'll have to practice how to use them to answer questions. So the exam for Chapter 4 and Chapter 5 is very concept heavy. Light on the math, heavy on the concepts. This table shows the distribution of electrons by energy level. So, in the 1s, that's within the energy level 1, we can hold 2 electrons. Let's make another column for total electrons. So right now we've got 2. The energy level 2 has the 2s and the 2p. The 2s, there's only 1 orbital, so we get 2 electrons there. In the 2p, we've got 3 orbitals, so we get 6 electrons there. So within the energy level 2, we can hold 8 electrons. So if we have an element that has both the energy level 1 and 2 filled, then we have 10 electrons total. What we're doing here is we're building up how to write an electron configuration. And the first step in doing that is knowing how to place the electrons into the energy levels and sublevels, and totaling up all of those electrons. Let's go one more. We'll talk through energy level 3. In energy level 3, we've got S, P, and D sublevels. With the S, there's always only one. So that means we can hold 2 electrons there. With the P, we have 3 of those orbitals. So we can have 6 of those. And remember, this is 2 electrons times the number of orbitals. Want to make sure that's clear. So in the s orbital, you can hold 2. In the p, there are 3 p orbitals. Whether it's 2p, 3p, or 4p, there's always only 3 p orbitals. And each of those orbitals can hold 2 electrons. With the d's, it's 2 electrons times 5 orbitals, and that gives us 10. So if we were to total up just all of the electrons we could fit in energy level 3, it would be 18. However, if we have an atom of an element that has everything filled from the 1s to the 3d, then we would take those 18 electrons and add it to what we have here for a total of 28 electrons. We're building. Let's continue. The electrons are arranged around the nucleus in a regular manner. You're going to fill the lowest energy levels first, which are closer to the nucleus, and then you start having electrons exist further and further away from the nucleus. Electrons are going to continue to fill each sublevel until it's full. Then you start filling the next closest sublevel. What's shown below is a partial list of the sublevels in increasing order of energy. I'm going to complete this list for you. If you have this list in your notebook, then you will be able to write out the full electron configuration of any atom of an element on the periodic table. In order from lowest to highest energy, we've got 1s, then you fill the 2s, you fill the 2p, the 3s, the 3p. Then we make a change. We fill the 4s first because it is slightly lower in energy than the 3d. And that is the trend when you start to have the d orbitals. Then you fill the 4p, the 5s, and then the 4d. So there's that change again. After the 4d, you fill the 5p, 6s, then we start filling the f orbitals. So the f sublevel is starting to be filled. Then you fill the 5d, 6p, 7s, 5f, 6d, 7p. And let's highlight those changes. So here we've got the 4f comes before the 5d, and the 5f becomes before the 6d. That's the complete list. With this list, you can again write any electron configuration. You just fill in, starting with 1s, and you fill each sublevel until you have no more electrons. One thing that we didn't talk about yet is that we've got these 2 electrons, let's say in the 1s. Electrons are both negatively charged, and like charges repel. So how do we handle that? The answer is the Pauli exclusion principle. And that pretty much says that if you've got 2 electrons that have to share an orbital, they're going to do so, but they're going to have opposite spins. We represent that by having an arrow going in one direction and an arrow going in the other. And that represents 2 different spins, so they can exist in the same orbital. The Pauli exclusion principle also talks about how electrons don't really want to share orbitals unless they have to. So let's look at this in practice. We'll go back to our friend carbon. We've seen this before. This is my hand-drawn periodic table, TM. That 6 tells us how many protons we have. And in a neutral atom, we can know how many electrons. So carbon has 6 electrons. These are my sublevels. So the first 3 sublevels in order from lowest energy to highest energy. I've got 6 electrons that I need to fill. Here's how we fill them. We're going to fill up the 1s completely first. That's 2 electrons. I have 6 electrons, so I need to keep going. Next, I'm going to fill the 2s completely, and I can fit another 2 electrons here. Now I'm at 4 electrons. Carbon has 6 electrons, so I've still got 2 more to place. Instead of filling in 2 electrons in the same orbital, the Pauli exclusion principle says I'm going to place them in 2 separate orbitals. So this is my orbital diagram for carbon. The 1s is completely filled. The 2s is completely filled. The 2p, I have 1 electron in 2 out of the 3p orbitals. Now let's say that we wanted to keep going. and we had our friend oxygen, which is a couple doors down. Oxygen has 8 electrons and 8 protons. We've got 6 in our diagram. So let's add on to make 8. The first thing we're going to do is add one more to fill out the p orbitals halfway. We've got 3 out of 6. We're up to a total of 7 electrons. Remember, 2 plus 2 plus 3 gives us 7 electrons. But oxygen has 8. We still need to fill in one more. That's when you go back and you start to fill in the opposite spin. So now we have oxygen. When we're writing configurations, we're not showing the spin, but we are showing the sublevels and the number of electrons in each sublevel. We always arrange the sublevels according to increasing energy. So you start with the 1s and you keep filling in order until you run out of electrons. If you want to say that you have 2 electrons in the 1s sublevel, the way you would write that is 1s and then a superscript for the 2. What that 2 says is the number of electrons in the orbital, or excuse me, in the sublevel. You have to write that, otherwise we won't know. All elements won't completely fill every single orbital. Maybe you have hydrogen. Hydrogen has 1 electron, so its electron configuration would be 1s1. So make sure that you write the number of electrons that are actually in that sublevel. Not the maximum, but how many you actually are holding in that sublevel. This is a periodic table, and what I'm showing you is the keys to the kingdom. Okay, we can break up the periodic table into blocks. I'm going to draw around this. This is the S block. And what that means is that the elements that I just outlined are filling their s orbital. Notice that the periodic table has rows. Each of those rows is a period that corresponds to a main energy level. So hydrogen is filling the 1s. Lithium, which is in the second period, is filling the 2s. Everything before the 2s is full. Beryllium is also filling the 2s. Everything before the 2s is full. let's say that we have something in the D block. That I'm putting in red. They're filling the D sublevel. Then we have the P block. And finally, the F block is down here at the bottom. So if you find your element that you're trying to write a configuration for, say, let's do bromine. Bromine is in the P block. That means that the last part of our configuration is going to be something in the P's. And we can literally walk across the periodic table, writing down each sublevel until we get to bromine. We'll start at the very beginning. We're at 1, that's the main energy level. S. The S can hold 2. And we know that we're holding 2 because we aren't even close to bromine. So the 1s is full. And I'll show you. I'm going to mark off each one. And let me modify this P block here. I don't know if I can without having to redraw the whole thing. Helium shouldn't be a part of that. Helium is really, it is a noble gas, which is why it's over here. But it's really part of the S block. So we've filled out the 1s. Then we drop down to the second energy level. Bromine is not in this row either. We don't see it in this period. So that means everything here is filled too. We've got the 2s, and we filled that with 2. 1, 2. We've got the 2p, because now we're in the P block. And there's 1, 2, 3, 4, 5, 6. 6 elements there. None of them are bromine. So we're still going. So all 6 of those spots are filled. So 2p6, that's what we've got. Moving on to the third period, the third row. We're back to the S block. 3s is filled. We go across to the P block, and that is also filled. Done. Now we drop down to the fourth energy level. Bromine is in period 4. So let's start to pay a little bit more close attention. The S block is completely filled. So we can write 4s2 and be happy. Then we've got the D block. Remember that 3D fills after 4s. So this is 3d10. We can cross all those off. And we're in the P block. We're back to 4. This is just to help ground you a bit. So we're in the 4p, and we need to count. 1, 2, 3, 4, 5. We counted 5 spots until we got to bromine in the P block. That means there are 5 electrons in the 4p. That is our configuration for bromine. Now, it took a bit to kind of talk it through, but if you walk across the periodic table and you know the order of all the energy levels, or you can just read it right off the table, then you can write the configuration quite easily. We'll practice this in class, and we'll also, if you want to, bring a periodic table to class, and you can label it like I do. We'll do it together in class. So if you like words, then here's a verbal/written explanation of how I just came up with the bromine electron configuration. Here's 2 problems that you can try on your own. We're actually going to go over these in class. So come to the live lecture for the answers to these. Try writing the electron configuration for a neutral atom of zinc, and it has 30 electrons. And then you can try writing one for neodymium, which has 60 electrons. Give it a try on your own if you'd like, but we'll go over these problems in class. The last bit of information I'm going to leave you with for Chapter 4 is what an orbital is and the different shapes of the orbitals. So an orbital is the region of space where there's a high probability of finding an electron. We don't know exactly what point in space where we're going to find that electron. Those electrons are zipping all around. But what we do know is probabilities. And electrons are more likely to be found in some places than others. Because remember, our energy levels are discrete, which means there's no continuous spectrum. Electrons are in this energy level, or there's nothing. The higher the energy of an orbital, the larger its size. So 4s is higher in energy than 2s. If I were to represent that, the s, which I'll tell you in just a minute, the s orbital is a sphere. So if that's my 4s, this might be my 2s. You can have electrons much further away from the nucleus. So remember that. We'll come back to that idea when we talk about periodic trends in Chapter 5. The s orbitals are spherical. And now we're in the quantum mechanical model of the atom. So Niels Bohr talked about the fixed energy levels. The quantum mechanical model says no, they're not fixed. Electrons can move from one orbital to another. They can increase in energy or they can release energy. So they can move around. They're not fixed. With the s orbitals, they're spherical. And the larger the energy, so 1, 2, and 3, the energy level, then the larger the sphere. Then we've got the p orbitals. There are 3 different p orbitals, and that really just talks about the geometry. So if you have a coordinate plane with the x, y, and z axes, then you can have the 2px, which has the 2p along the x-axis, 2py along the y, 2pz along the z. So when you put them all together, then you get the whole orbital set. The p orbitals are shaped like dumbbells. Everywhere that you see green, that's where you have a higher probability of finding an electron. Then we have the d orbitals. 4 of these d orbitals have a cloverleaf shape. Then there's one kind of weird one, and that one has like a dumbbell that's going through a donut. So it's kind of reminiscent of a p orbital that's got a ring around it. We're not going to talk about the f orbitals. That's it for chapter 4. Thanks for watching. This is a very abstract chapter, so it's going to take some practice and practice problems. Make sure that you come to live lecture and do the practice problems. Really engage, because otherwise these details aren't going to make any sense. And when you come to the exam or the homework, you're going to be lost. So make sure you actively participate in live lecture. That's where we do all our practice problems. And you'll get details regarding assignments and exams. I always talk about the types of questions you'll see on exams. I really give you the keys to the kingdom. So come, participate, take notes, ask questions. That's what I'm here for. As always, stay safe, and I'll see you in live lecture.